Let's look a little bit at how we can measure radioactivity. There's a few different ways to look at it. We can look at it more from the point of view of the sample itself. How many atoms are disintegrating per second? So that does not relate the activity to the effect on people at all. Just the atom itself, how fast is it disintegrating? So a becquerel is 1 disintegration per second. So if you had just 1 becquerel of activity, only 1 atom of your sample would be disintegrating every second. So this is pretty small. Usually things are in the 1,000 to 10,000 becquerel. For a significant amount of sample, it will be disintegrating thousands of times per second. A curie is a much bigger unit. A curie is another unit of disintegration. It's on the order of magnitude of 10 to the 10 becquerels. So that is, historically, it came from the amount of activity you could expect from 1 gram of radium. Radium is an element discovered by Marie Curie. So 1 gram of that emits 3.7 times 10 to the 10 disintegrations per second. So that would be 1 curie. The next 2 units relate the amount of activity to its effect on biological systems like people. So the absorbed dose is really a measure of the amount of energy that's being absorbed by biological tissues. So that unit is rad. That stands for radiation absorbed dose. And there's another unit that you could measure absorbed dose in, and that is called a gray. The relationship between those is that a gray is equal to 100 rad. Then the third unit is one of biological damage. So if a tissue does absorb energy, these are related, so they're proportional to each other. The more energy is absorbed by a tissue, the more damage it's going to experience. However, there are some, the different types of radiation can do different types of damage to biological tissue. So for example, I just have a little graphic up here. Your textbook has some more information and some better pictures, but alpha particles, since they are large, they're helium nuclei, as opposed to a beta particle, which is just an electron. It's much tinier. So an alpha particle, when it's traveling in the air, it tends to hit something sooner because it's bigger. So it's kind of like having a very large vehicle try to maneuver through traffic versus a smaller vehicle can kind of whip through a little bit farther and a little bit faster. So the alpha particle can be shielded by paper. So you can block alpha particles if you have alpha radiation. That can be blocked by paper, clothing. So it doesn't take much to stop alpha radiation. Beta is a little bit more difficult to stop. You maybe need some plexiglass or some other kind of shielding. If it gets into tissue, it can get in the first few millimeters or so, whereas alpha particles usually can't get very far. Your skin will block the alpha particles as well. Beta can penetrate a little bit further into tissue. Gamma being pure energy, if you wanted to block some gamma radiation, you would need cement or lead. So you'd need a pretty substantial shield to block you from gamma radiation. However, the alpha particles, even though they are easily blocked, if they do get into tissue, since they are larger particles, they do cause more damage. So biological damage for alpha particle would be at least 10 times the amount of damage you would see for a beta particle. So the REM, which is the Rontgen equivalent in man, the damage that would be caused are the rads multiplied by some sort of biological factor that depends on the type of radiation and the type of tissue that is absorbing that radiation. So these are related, but they have different units because they are a little bit different. So we have REMs, and sieverts is another unit that you can use to measure damage. So we have the energy being absorbed by the tissue and the damage being caused to the tissue have 2 different units because they're slightly different things that are being measured. And we have a relationship here between rems and sieverts. So we can practice with all these different units and doing some unit conversions. So the questions in this section of the chapter have to do with interconverting units. So this is a good opportunity to practice that since we're learning a few different units here and we have a few different relationships. Also, I do want to emphasize that we should not forget what these metric prefixes are. I know that we had those in a quiz a little while back, but we do want to keep those in mind. So rem and millirem have a relationship based on the metric system. Let's go ahead and write that relationship. So 1 millirem, remember that milli equals 10 to the negative 3, so 1 millirem is 10 to the negative 3 rem. And then we also have the relationship that 1 sievert is 100, put a decimal here to show that this is a 3 significant digit relationship, 100 rem with 3 significant digits. So let's go ahead and do a conversion and find out how many sieverts a dental x-ray will cause. So starting with 20 millirem, 1 millirem is 10 to the negative 3 rem, and then 1 sievert is 100 rem. So this will cancel millirem and it will also cancel rem. So that leaves us with sievert. The other things that are left are the 20, the 10 to the negative 3 in the numerator, and the 100 in the denominator. 20 divided by 100 is 0.2. We also had a decimal after the millirem, so we have 2 significant digits there. So we have 0.20 times 10 to the negative 3. 0.20 is the same as 2.0 times 10 to the negative 1 times 10 to the negative 3. So that is 2.0 times 10 to the negative 4 sievert. Or if you did not convert to scientific notation, it should be 0.0020 sievert. So we just have some powers of 10 changes going on here. All right, speaking of powers of 10, we have Curie's and Becquerel, which is a fairly large number in our conversion factor. Let's go ahead and write our metric conversion. A millicurie is the same as 10 to the negative 3 curies. And then a curie is 3.7 times 10 to the 10 becquerel, so quite a number of becquerel. Those are our relationships. Let's see if we can set up our conversion factors. So we have 12 millicuries. I'm going to go ahead and use this first relationship that 1 millicurie is 10 to the negative 3 curies. That will convert to curies. And then 1 curie is 3.7 times 10 to the 10 becquerel. Let's check our units here. Our millicuries cancel and our curies cancel, and we're left with becquerel, which is what we wanted. I'll also put our significant digits here. We have 2 significant digits, infinite for the metric conversion, 2 for the becquerel conversion. So we're going to have 2 in our answer. Let's gather what we have here. We have 12 times 3.7. I'll just put our regular numbers here. Now I'll put the powers of 10. We have 10 to the minus 3, and we have 10 to the 10. And then we have becquerel as the units. 12 times 3.7 ends up being 44. 10 to the negative 3 times 10 to the 10 is 10 to the 7. This is almost ready, but it's not quite scientific notation. 44 is the same as 4.4 times 10 to the 1. We'll bring down 10 to the 7. and we get 4.4 times 10 to the 8th becquerel, which you might have gotten just by putting these things into your calculator. If you are good with using scientific notation on your calculator, you could have done that as well, but you should have 4.4 times 10 to the 8th becquerel as the answer. All right, so the rem and sievert units were ones that had to do with the biological damage of the radiation dose. And so just to give you an idea of what levels we need to worry about, if you have less than 25 rem, which is less than 0.25 sievert, then that is usually not detectable. So you won't even notice being hit by that amount of radiation. When you get a little bit higher here, the first effects are reduction in the white blood cell count. And then these mid-range radiation levels are the types that unfortunately you might know someone you might be familiar with. The radiation sickness, if you have to have radiation treatment to counteract cancer, that's one of the possible therapies. And so that type of radiation does do damage and cause these ill effects. So the cancer cells are being killed, but these other fast-growing cells are also affected. So your intestines give you some intestinal issues, nausea, diarrhea, vomiting could be some of the results of that. Definitely fatigue. Hair follicles are also very fast-growing cells, so they're very sensitive to radiation treatment as well. So these types of results will happen for that amount of radiation, whether it's through a medical treatment because of cancer or through some other sort of accident. This amount of radiation damage would have that effect. Then a fairly high dose of radiation, 500 rems or 5 sieverts, is the LD50 for humans. LD50 stands for lethal dose in 50% of a population. So if you are talking about any kind of poison or any kind of damaging factor, anything that would kill half the people that had it happen to them is called the LD50. So LD50 for radiation is about 500 rem. And then if you get much higher than that, 600, then you get not just 50% lethal, you get fatal to 100% of people that are exposed to that amount of radiation. So let's take a look and see for 3.5 times 10 to the 5 micro rem. Let's take a look at what sort of biological effect it can have. Since our chart has just rem instead of micro rem, let's try to convert this amount to rem so that we can then take a look at the chart. Micro is another one of our metric prefixes that we should still be able to know how to use. Micro means 10 to the minus 6. So 1 microrem is 10 to the minus 6 rem. Let's use that relationship to convert this. 1 microrem is 10 to the minus 6 rem. We'll cancel the microrem. So I went ahead and collected everything together, the 3.5, the 10 to the 5, and the 10 to the minus 6. So now I will multiply together the powers of 10. So that gives us 3.5 times 10 to the minus 1 rem, which is 0.35 rem, which is a very small dose, way less than 25. So this would be not detected. So the effects of this are so small that nobody is going to even notice. Does not do any significant damage to the human body.